The Gauss law or Gauss theorem is a very important law in this chapter of electrostatics. And it's not a very difficult law, it is quite a simple law. And I want you to understand this law nicely. So, first of all, let us look at the statement of this law. According to this law, the total flux through a closed surface called Gaussian surface is equal to 1 by epsilon naught times the net charge enclosed by the surface. That is, flux phi E is equal to Q by epsilon naught, where Q here is the net charge enclosed by the surface. Or in integral form, we write integration of E dot ds is equal to Q by epsilon naught. All right. Okay, so let us prove this law. Let's say we have a small point charge out here plus Q. So what will happen here, this point charge, it will emit or it will produce electric field in all directions. So the electric field lines will be going out in all directions. So what we do is we choose a closed surface. Okay, and the shape of this closed surface, for convenience, let us choose it to be a spherical surface. Okay, so let's say something like this. We have a spherical surface which is enclosing the charge. The charge is at the center of this spherical surface. Got it? And what is the name of this spherical surface or this closed surface in general? This is the Gaussian surface. All right. So the Gaussian surface, it can be of any shape, doesn't matter. It can be of any shape. I've just chosen a spherical shape just to make our proof easier, but it can be of any shape. It can be a cube, or it can be a cylindrical shape or any irregular shape as long as it is a closed surface. Okay, so I've chosen a Gaussian surface in the form of a sphere. Let me write down the name of this: Gaussian surface. All right, and let us find the flux passing through the Gaussian surface. Okay, so I imagine that there is a point here, a point P. Okay, a point P somewhere here, and the distance from P to the charge plus Q is how much? That would be equal to the radius of this spherical surface R. Okay, so we choose a small area here. We choose a small area out here. Okay, and the area vector of the small area is pointing in which direction? It is pointing in that direction. This is the area vector ds bar. Got it? What is ds bar? It is the vector representing this small area element out here. And what by definition, this area vector is perpendicular to this small shaded pink color area. Okay, and what will be the electric field passing through this point Q? Coming from this point Q and passing through this area. The electric field will also be in the same direction as this area element. Yes or no? Because the electric field comes out like this, it goes in that direction. So at this point, the electric field will be in the same direction. Okay, let's call this electric field as E bar. All right. Okay. Now the electric field intensity, the electric field intensity at P is given by what? We already have this expression. E bar modulus is 1 by 4 pi epsilon naught Q by distance square. And what is the distance from P to the charge Q? That will be R. So this will be R square. Call this some equation 1. Okay, right. So now let us find the electric flux. Let me take another page. Therefore, total flux passing through the Gaussian surface is what is integration of E dot ds. So let us apply the A dot B formula. We know that A dot B is how much? A dot B is equal to AB cos theta. Yes, what is theta? Theta is the angle between A and B. So here E dot ds, this will be E ds cos theta. Theta again is the angle between E and ds. And if you look at this diagram, what is the angle between E and ds? Between E and ds, are they not pointing in the same direction? And because they're pointing in the same direction, they're parallel, their angle will be 0. So therefore, this will be cos 0 degree. All right. So you have E ds. Since this part cos 0 degree, this is equal to 1. Okay. Right. So now let us put the value of E from the equation 1. E is 1 by 4 pi epsilon naught q by r square ds. All right. So if you look at this integration out here, the integration is done with respect to ds. Okay, which means that these terms are all constant, independent of ds. So what do we do when we integrate like this? We put the constant term in outside of the integration sign. So this q by 4 pi epsilon naught r square will come out of the integration sign. Then we are integrating only ds over a closed integration. Got it? Now what is the value of this integration out here? How do we know the answer? Look at this. When we take integration of ds, that means we are integrating this small area, and integration basically means to sum these tiny small areas, right? So if we take these small areas, and we sum the small areas, are we not getting the entire area of the sphere? Yes, when we integrate this small area, we will get the entire area of a sphere. And by formula, the area of a sphere is how much? I think you know this very well. The area of a sphere is 4 pi r square. Okay, so you get q by 4 pi epsilon naught r square into 4 pi r square. So 4 pi and 4 pi will be cancelled. R square and r square will be cancelled. So therefore you get E dot ds is equal to q by epsilon naught, which is the proof. Some important points to note. Now in the Gauss law, we have E dot ds. E dot ds, this is equal to q by epsilon naught. Now this q out here, this q is actually the algebraic sum of all the charges inside the Gaussian surface. Okay, so the word here is inside. That is the important word here, inside the Gaussian surface. Right, so basically this is actually the net charge. All right, so I can just write here q net. Okay, the net charge enclosed by the Gaussian surface, or the net charge inside the Gaussian surface. And how do we get the net charge? We take the algebraic sum of all the charges. For example, let's say I have a Gaussian surface. Let's say I have a Gaussian surface like this. Now, like I told, the Gaussian surface, it may be of any shape. It may be a geometrical shape or any irregular shape, as long as it is a closed surface. Now inside here I have a number of charges. Let's say I have plus q1, and then I have plus q2, then I have here minus q3, and let's say minus q4. Then outside I have a plus q5, and another charge here minus q6. Okay, so according to the Gauss law, integration of E dot ds, that means the electric flux, this is equal to the algebraic sum of the charges which are only inside. That means q5 and q6 are excluded. Alright, so how do we get the net charge? We just take the algebraic sum. So q1 plus q2 minus q3 minus q4 whole thing divided by epsilon naught. Got it? So this is what the law says. So that's the first example. Another example, let's say example 2. Okay, let's say inside of a Gaussian surface we have an electric dipole. Okay, we have an electric dipole. An electric dipole basically consists of two charges, plus q and minus q charges. Okay, so what will be the electric flux passing through this Gaussian surface? So the electric flux E dot ds, this will be the sum of the two charges q and minus q divided by epsilon naught. So this will be 0. Right? Why? Because the net charge enclosed by the surface is 0. Okay, so that is the first important point to note. Got it? Secondly, the shape of the Gaussian surface is not defined. Okay, it can be any shape, which means that it can be any shape as long as it is a closed surface. All right, so you can take the Gaussian surface depending on the geometry of the problem. For example, let's say if you have a line distribution, okay, a line distribution of the charge. Let's say on this wire you have the positive charges which are distributed uniformly. Alright, so if you can take, now the question is, what is the shape of the Gaussian surface to be taken? Now if you look at this wire, if you cut the wire, okay, if you cut it into a very tiny length, okay, now if you expand this, you will see that the shape of the wire is something like this. It looks almost like a cylinder, right? In fact, it is cylindrical in shape. So therefore, the Gaussian surface to be taken also, you can take it to be cylindrical in shape. Alright, so you can take a cylindrical Gaussian surface like this, whose axis is parallel to the wire. Okay, or maybe if you have, let's say, a spherical distribution. If you have a spherical distribution, let's say you have a sphere, like this, and on this sphere you have the many charges sitting on the surface of this sphere, then what type of Gaussian surface are you taking? You will take, looking at the geometry of this problem, you will take a spherical Gaussian surface. Understand? So it doesn't matter whether you're taking a cylindrical or a spherical or maybe a cubical Gaussian surface, as long as it is a closed surface. Alright, so those are the important points to note when we deal with Gauss law.